Good afternoon, everybody. Usually the kernel talk takes place at DebConf, but this year, as a special treat, it will take place here in Toulouse at this MiniDebConf. So I would like to introduce the speaker, Ben Hutchings, who does kernel things. Oh, wait, one more latecomer. Just give you a moment to sit down. Everybody ready? Let's go.
Hi, welcome. I'm going to talk about what's been happening in the Linux kernel over the past year or so, and some of the things that still need to be done in Debian to take advantage of those changes. I have been working on the Linux kernel and the software around that, both for Debian and in my paid employment for around 15 years now. Most of my work in Debian is as part of the kernel team and also the LTS team. I do all kinds of packaging tasks, review other people's changes, and do a certain amount of backporting fixes. The Linux kernel keeps on changing at a fairly rapid pace. Linus Torvalds makes a new stable release with new features roughly every 9 to 10 weeks, so 5 or 6 times a year. However, larger features may be too large to get into a single release cycle, so they may take several releases to become useful. And some features need changes outside of the kernel to enable them, possibly a new tool to manage that from user space, or a later version of an existing tool. Sometimes there will be a new API that's generally useful for applications and libraries, so those will need to be changed to take advantage of it. And sometimes we need to make packaging changes or even infrastructure changes in Debian. In this talk, I'll be covering the new features since my last talk, so in releases 6.6 to 6.12 inclusive. 6.12 isn't out yet, but I think will be out tomorrow, and we know what's going into it. So a recap of some of the features that I've talked about in previous years that had ongoing development. The RISC-V architecture is no longer so new. In fact, I think that's likely to be a release architecture for Debian 13. In the kernel, there's now support for performance counters, which are great for performance analysis of both kernel and user space code. It supports suspend to RAM, which I guess will be useful once we have RISC-V laptops. The mem barrier, system call, memory hot plug, kernel address space layout randomization, which is an important security hardening feature. Control flow integrity, which is another hardening feature. Unfortunately, that's currently relies on the Clang compiler, which we're not using in Debian. And you can build drivers in Rust for RISC-V. The I/O U-ring, asynchronous I/O API, supports some additional operations. So that becomes increasingly useful for doing all your I/O. ID mapped mounts, which are useful for containers, depended on those needed support both in the generic file system code and in each specific file system. So those are now supported on Fuse, HugeTLBFS, and ZoneFS file systems. The uBlock facility, which allows you to have block drivers in user space similar to Fuse, that's now enabled in the Debian kernel configurations. However, we're still missing the uBlock serve software that's needed to configure that. I opened an RFP for that earlier. That's been changed to an ITP, and there is some packaging work linked from that bug, but it hasn't been uploaded. So if anyone's interested in that, maybe get in touch with the developer and try to get that uploaded. I talked about doing HID drivers or HID quirk handling in BPF. HID is the is the protocol used for input devices attached via USB or Bluetooth. Currently, there are a lot of. It's a standard protocol, but a lot of devices are a little bit buggy and need some slight tweaks to the handling in the kernel. The idea of HID BPF is to make it easier to add that quirk handling without needing to write a whole driver. That's not yet enabled in Debian. We would need to do some packaging work to actually build the in-tree BPF programs for that. And then Rust, which is a safer system programming language that is becoming increasingly useful in Linux. There's now support for writing Ethernet PHY drivers and block drivers in Rust, but overall progress has been slow. The well-known drivers, like the one for the Apple GPU, they're not yet upstream. There isn't support for doing GPU drivers. And then kernel space TLS, which is useful for networked file system and block protocols that are implemented in the kernel. That's now supported for NVMe over TCP. I've got a few slides here about changes in file systems. Firstly, bcachefs. It's a new, not entirely new file system, but it's new upstream. It's a fairly modern design that's competing with Btrfs and ZFS and has a somewhat similar feature set. So the contents of files are shared copy on write, allowing for fast snapshots and file copies using the reflink system call. It does full checksumming of both metadata and file contents. It has an option for data compression and an option for full disk encryption. Now, this is done using the authenticated encryption mode, AEAT, so that avoids some of the weaknesses of full disk encryption done at the block layer, like with dencrypt. It doesn't support the fscrypt API for file system layer encryption, though. Like its competitors, it can also use a pool of multiple devices. As the name suggests, it's partly based on the bcache disk caching subsystem, which means it can make effective use of faster and slower devices, such as an SSD for hot data and a hard drive that's slower, bigger and cheaper for the cold data. Currently, that's marked experimental, but it is already enabled in Debian kernel configurations. So it's possibly not something you want to trust all of your data to quite yet. There have also, unfortunately, been some interpersonal issues between the upstream maintainer and some of the other developers that he needs to work with, which might be a risk to this, to the further development of the file system. Some smaller changes. We have new system calls, list mount and stat mount, which can provide structured information about all the file systems that are currently mounted. That information is also available in text format in proc self mounts, but there are issues with text-based formats and correctly representing arbitrary strings in there. And the structured information is probably a lot easier to use for programs written in C and similar languages. There are some new generic ISCTLs which you can use on many different file systems to get the UUID of a volume or to find out where that volume's metadata lives in sysfs. The tempfs RAM file system has support for user extended attributes and quotas. So I guess if you have a Timberfest mounted on a multi-user system, you can use quotas to stop your users from filling up memory. The XFS file system has gained support for online repair of some file system errors, so it's possible to scrub and repair without unmounting. The generic file system code, known as VFS and XFS, now also have support for file system block sizes being larger than the system page size. Previously, the kernel had an assumption that it was always possible to write back data from memory one page at a time, and that just doesn't work if your block sizes are larger. Now, apparently that works. The ext2 driver is now deprecated. It doesn't support timestamps beyond the year 2038, the 32-bit timestamps. That doesn't really matter that much for Debian. We're using the ext4 driver for volumes in ext2, 3, and 4 formats, and that has a minor extension that allows for later timestamps. However, older volumes that were created with 128-byte inodes will have this problem and will all need to be replaced before the year 2038 comes around. The old in-kernel NTFS driver has finally been removed in favor of the newer NTFS3. Currently, neither of those is enabled in Debian. We had concerns about how well they were actually being maintained and a number of security issues in those. So the default implementation in Debian is NTFS3G, which is a fuse-based implementation. I think at this point NTFS3 looks like it might be safe to enable, though. Right, so the real-time patch set has... well, first, let me talk about what real-time actually means. In a real-time system, the time it takes to respond to high-priority input has an upper bound on it. You can guarantee that that you will respond to that high-priority input quickly enough, and that requires tasks to be strictly prioritized or to have guaranteed CPU time so that they can meet that guarantee. This is essential for many safety-critical systems, such as for vehicle electronic control and industrial process control. And it's also good to have if you're doing live production of audio and video. Real-time system isn't necessarily fast in the sense of most benchmarks. It tends to have worse throughput, and also the average latency may be worse, even though the worst case latency is lower. So for around 20 years there's been an out-of-tree patch set for Linux, known as either Linux RT or preempt RT. It adds a configuration option, config preempt RT, and what that does is to change interrupt and soft interrupt handlers to become schedulable tasks. So they can be preempted and they can be prioritized just like regular tasks. Most of the kernel locking then can also leave preemption enabled, and the result is that the non-preemptible sections of code in the kernel are relatively short, and that in principle allows you to have that bounded latency that's needed. There's support for both prioritized scheduling and deadline scheduling, which is the mode where you have guaranteed CPU time or CPU bandwidth for specific tasks. A lot of the changes that were done through this patch set out of tree turned out to be generally useful. They've already filtered upstream and are actually used in all configurations. The config preempt RT option was eventually added upstream quite a while ago in Linux 5.3. However, at that time, it was dependent on each architecture to declare this architecture is ready, and at that time, no architectures did that, so it wasn't something you could really use. However, in Linux 6.12, all of those necessary changes are upstream for a couple of architectures, ARM64 and x86. The out-of-tree patch set is still needed for ARM, 32-bit ARM, and for PowerPC, and to fix some issues with the i915 driver on x86. Debian has been providing kernel packages with this patch set and config preempt RT enabled for several of those architectures since version 7 Wheezy. But hope I don't have to remind you, but some people seem to be confused. Debian comes with no warranty, so these packages and Debian in general should not be used in safety critical systems. So some changes in the Linux security modules. Linux security modules are a mechanism for putting in security policy and security restrictions that are separate from the classic Unix file permissions. So the landlock security module has been around for a while now. It's a way for user processors to restrict themselves, also known as sandboxing. And this is not an alternative to the sort of system policy you can get from AppArmor or SE Linux. It's complementary to that. You can also do sandboxing with the setcomp system call, which limits which system calls and parameters a task can use. I would say it's complementary to that as well. There are some things that landlock can do and setcomp can't, and vice versa. So over the last year, landlock has gained the ability to restrict use of TCP ports, both as a client that connects to specific ports or as a server that binds to ports and listens. It can also disable most IOCDLs on devices that a process has access to, for example, the TTY device. And it can restrict access to so-called abstract Unix domain sockets. On Linux, Unix domain sockets can live in the file system, and then you can restrict access with file permissions. But there's also an abstract namespace where you don't have that ability. So with landlock, you can apply some restrictions. The AppArmor security module can now restrict the use of IOU ring and user namespaces, which are both very useful but very powerful features that have had a number of security issues with them. So that could be useful for reducing the kernel attack surface. There are also some new system calls for configuration of Linux security modules. This is intended to be a generic API that will work across all of the many LSMs that currently exist. It can expose process attributes from multiple LSMs, which currently isn't possible through the proc file system. This is preparation for the ability to stack major LSMs. Major LSMs are AppArmor, SE Linux, SMAC, and Tomoyo. Currently, you can only have one of those active on the system. But if you wanted to run a Debian system container with its AppArmor policy on top of a Fedora host that uses SE Linux, currently you can't do that. There is a plan to enable that stacking, and this API is preparation for doing that. And then there have also been some changes in security hardening of both the kernel itself and the features that support user space hardening. At this point, it's very difficult to inject arbitrary code into the kernel. So a lot of attacks rely on things like heap use after free. So if the kernel allocates one kind of object, frees it, but still has a reference to it, sometimes it's possible to create a different type of object in that same memory. If the contents of the second object are controllable by the attacker, then that can lead to extremely bad results. So this kind of problem is called type confusion. And we have two mitigations for that now. One of those is there's a compile time option to randomize the way the kmalloc API caches those free caches the list of free memory. So that's a global option. It's probabilistic, that is, it reduces the chance that an attacker is able to exploit this kind of bug, but it doesn't eliminate it. There's also a new kernel API for what's called dedicated slab bucket allocator, and that provides full mitigation, but because it's a new kernel API, it requires each caller in the kernel to be updated to take advantage of that. And in user space, one of the ways to attack another process is to write to its memory through the proc file system. And currently, by default, you can actually write to read-only memory that way, including the code of the process. So there's now a compile time option and a boot time option to disable that. Unfortunately, it's not enabled by default because some programs do this. Some programs do this to themselves. I think for some just-in-time compilers do this. So there are some compatibility concerns, but if those don't apply, then that's something you can turn on. There's a new system call, mseal, which comes from the Chromium developers, and that allows user space to lock down a memory mapping. So in future, if that process is exploited, it still can't change the memory mapping. And finally, on x86, we have support for Intel shadow stacks, finally. And with shadow stacks, the return addresses of function return addresses are stored to a separate area of protected memory. And that means that stack smashing attacks can't overwrite them. So that protects against attacks in user space. Shadow stacks are not being used in the kernel itself. Finally, packaging changes. There have been quite a few changes in the Linux package. We have some updates to the supported architectures and flavors. On ARM64, we have a new flavor that uses 16 kilobyte pages for memory management. This should be good for performance of at least some applications. It's also going to be essential if we support the Apple M series processors in future. We're building a kernel for the Lunarch 64 now, and on MIPS64EL we have a kernel flavor built for our revision 6 CPUs. On PowerPC 64 and both big endian and little endian variants, historically we built the kernel using 64K pages for memory management. This is not compatible with all drivers or all user space programs. So we've now changed the default to be 4K pages, similar to most other major architectures, with 64K pages remaining as an alternative flavor. On ARM-EL, we've had to drop the Marvell kernel flavor, which was used for various NAS systems using Marvell chips. A lot of those have a limited space for storing the kernel image, and we were no longer able to squeeze a useful kernel into that space. The Intel Itanium or IA64 architecture is finally gone, both upstream and in Debian. And most significantly, we're no longer building i386 kernels. So you can still run a i386 user space, but you'll need to have a 64-bit kernel. There are a couple of new minor binary packages. Linux BPF-dev is providing a necessary header file for building BPF programs in the compile once, run everywhere mode. And on x86, there's a tool for... Intel has some value-added features on their CPUs, on some of their high-end CPUs now that require an extra license after actually buying the CPU. Intel SDSI contains the tool that you'll need to do that. The Linux libcdev package that contains the kernel user space API headers is now architecture all instead of being built for each specific architecture. The intent was that this would make things easier for bringing up new ports, but it's not entirely clear that it has made that easier at all, so that might change back. We've basically given up on trying to maintain the kernel module ABI. We used to name kernel image and headers packages using a Debian-specific ABI number, but we would change every time that the kernel ABI changed, and we're no longer doing that. We're just using the upstream version. And all of the architecture-dependent packages, all the architecture-dependent binary packages are now cross-buildable. Actually, that's a slight lie. I have a merge request open that will fix the last of those. Right. We've made configuration changes to improve support for a whole lot of hardware. Intel Meteor Lake SoCs and the image processing units that are present on a lot of recent Intel chips. System 76 systems, Chromebooks, Chrome OS tablets, a few ARM-HF devices, lots of different ARM64 SoCs, the Raptor Telos 2 PowerPC system, and on RISC-V64, the Microchip Polarfire SoC, Softco and T-Head SoCs, and we've improved support for some Star5 devices. We're signing modules on all architectures, and you have the option to enable lockdown. Lockdown is activated by default if secure boot is active, but there's also a command line option to turn it on if you want. We build mostly reproducible again. Currently, module signing is a blocker for that because it generates an ephemeral key at build time. I have some ideas for how to tackle that, but haven't yet found the time to implement that. Modules are installed compressed, which hopefully reduces the amount of storage space wasted on drivers you're not going to use. The continuous integration configuration now includes a quick build for ARM64, as well as AMD64. And we've had a whole lot of changes to the internal configuration of build system, which seem to make things a bit cleaner. So it looks like we have a bit of time for questions. 10 minutes.
Question, which compression are you using for the modules? Is it ZSCD or is it something else?
It's XZ currently.
Okay, thanks.
Mic 2, please. I've been using this FireJail thing, which uses user namespaces to do security. But is it a good idea? I don't know. What do you think? I mean, is it more risk than gain, or you gain security?
I think early in the lifetime of user namespaces, it was a bit risky. We made the decision, I think, leading up to Bookworm, that probably there was more benefit from the sandboxing potential of user namespaces than the risk that they added. I don't know if that's true, but that's the decision we made.
Okay, thank you.
There was also a question of IRC. So I just repeat a question from IRC. How do you see building Rust drivers, notably the need for a very recent Rust compiler?
Yes. I think this is something we're going to need to think about in the next release cycle. At the moment, there aren't really any interesting Rust drivers upstream. That's going to be a challenge, I think, to build those. But we'll need to look at it for whatever it is comes after Trixie.
Thank you. I've tried to look it up, but didn't quickly find an answer. Do you happen to know whether the UBLK driver will be unable to be useful in user namespaces, unprivileged ones? Or is that initial user namespace root only capability?
I would guess not.
Thank you.
But I don't know.
Wasn't there a second question on IRC?
Yes. The second question from IRC, it is about if you could share some of the ideas for reproducibly building the kernel modules.
I didn't quite understand that.
It was about how you could reproducible build the kernel modules,
right.
probably
Okay,
regarding the
yes.
signed kernel modules. And,
Okay, so several people have independently come up with the idea that you would basically take a hash of all the modules built in tree, then add that into the kernel image, and then that would be an allow list of the modules, and then you don't have anything random in there. It's also an awful lot simpler than public key cryptography.
Thank you. Another question, maybe? Yep.
If I want to enable Linux RT, would I just have to install Linux image RT AMD64, or would I need to
Exactly.
take all the steps? Maybe I should change the bootloader to tell it to boot the RT kernel, or would that be done automatically?
I think that would happen automatically, I think, because the kernel name would sort as a higher version.
Okay, thanks.
Do we have plan to solve the problem between EFI and real-time kernel? The symptoms are, for instance, that when you install a airtight kernel, you could not boot it because grub refused to install because EFI variables are not available. So we need to add a command line to the kernel.
Yes, right. I am aware of this problem. I can't. I think there was some. I think there was some work upstream on having the option to still enable EFI variables.
Yes, but we need to add manually. Yes, but it's not automatic. It's manual stuff, and it's not really user-friendly.
Yeah, we have the same problem in Ubuntu, which is real-time now is integrated, so we don't have a separate kernel. What we're planning to do, and I think what is already supported upstream, is to set some variable and be able to apt install Linux real-time. And this would add an option in etc grubd, create a file like 99 real-time or something, which will add the option to the command line. The only problem we have is this would only support grub, but we need to take care of other bootloaders, which would be systemd-boot, which already supports something named etc cmd line, which is something grub doesn't support. So maybe we need to patch our Debian grub to go read etc cmd line so that grub can integrate something that the...
I've been thinking for a while. We actually need to have some. We need to have some common system for where packages can drop extra command line arguments that would be supported by all bootloaders.
In Ubuntu, we're going to take the initiative of creating, I think, etc cmdline.d, and then people could add some files here. I think we should patch the Debian grub so that the Ubuntu grub, the Debian grub, and also maybe go patch systemd-boot. So instead of reading etc cmdline, you could read etc cmdline.d, and then we could add multiple files here to easily change the command line thanks to packages instead of manual editing.
That would be awesome if we could get that coordinated. If you could do that.
I'll try to work with the Debian grub 2 people then. Thanks.
Talking about CI, currently, as mentioned, AMD64 and ARM64 run quick builds. There are things to be improved that could be done on Salsa, not in Salsa CI, or even that could be also in the ARM runner or on Salsa.
Mostly, I would just like to see faster runners and more of them.
Okay.
So with the quick builds. With the quick build, we're just building one flavor of the kernel for each of those architectures, and it's the cloud variant, which has very few drivers enabled, and that allows us to get a kernel build done in an hour or so, which is still pretty slow, I feel.
Thank you. There's still 1 minute left if you have one last question. So thank you very much, Ben.